Hey Nick, I'm going to work through a problem that's like the one in your homework that you sent to me in your email, having to do with being given a couple of zeros for a polynomial that has several zeros, and how to use the zeros that you are given or that you know about to find the remaining ones. So it's kind of like a number where if you know some of the factors of the number, you can divide that number by the factors that you know, and that gives you a smaller number to kind of continue to break down. So let me show you the one I have already kind of figured out for us here. Hang on, I'm trying to share the thing. Hang on, share it. Here. Okay. Sorry about that. Okay, so this is similar to the one that you did. I just built a different one so that you could take this example and go back and work the problem that you sent me. All right, so what's happening if you look at this is there's a polynomial that's been given. It has a fourth degree, which means it could have as many as four separate little binomial factors like x plus 3, x minus 2, x plus 7, x plus 8. I'm just making these up, but you could have as many as four different little factors that when you multiply that whole mess together, this is what you end up with. So we're trying to find all four of those factor pieces. Each factor relates back to a zero. So we've been given two of the zeros. So it says two of the zeros for this one are -1 and +2. So if you're given zeros, that just means this is the number that you got when you set that associated factor equal to 0 and then solved it for the x. So if you end up getting -1, that means our factor must have been x plus 1. So if the 0 is -1, the associated factor would be x plus 1. So the same thing over here, if they give us another 0 as x equals 2, the associated factor that goes with it would be x minus 2. Again, because if I take and set x minus 2 equal to 0, to solve that, I would have to add 2. And that's what I would get. That's what a 0 is. Okay, so anytime you're given a 0, or then maybe they call it an x-intercept, you change the sign of the number, and that becomes what you put in with the x to form a factor. So if I multiply these two factors together, that would give me some kind of a quadratic that has x squared plus or minus, I don't know. We're going to figure it out in a minute. And that would be two of the four factors that we're looking for from this one. So let's first of all multiply it together and see what larger factor that can produce. So it's like if I knew that 2 and 3 both divide into a number and I want to know what's left after I divide them out, it would be easier just to divide that bigger number by 6, the product of the individual factors, rather than divide it by 2 and then divide it again by 3. So we're going to multiply these together first and find the larger quadratic factor so that we can then do long division between this quadratic factor that's formed by these two divided into our original really big fourth degree one, Quartic. Okay, so to do number one, the first thing we'll do is multiply the two individual factors together to get a larger factor that we can use for polynomial division. So this will give us x squared, that'll give us -2x plus 1x. Will give us -1x. I'm just doing a FOIL here, and then 1 times -2 would be -2. So that's just running it in reverse. If I needed to factor this quadratic, this is what it would produce. Right now I have the two factors, and I just want to get a bigger polynomial so that I can do the division all at once. I could also do a polynomial division over and over again by first using this one as a divisor and then taking that result and using the next one as a divisor, but this will just get to it faster. So what I'm going to do is take this big polynomial, divide it by this piece, and the result should be another expression with x squared in it. So let's do a big quadratic divisor out here. This is what we're dividing by, because it's got a smaller degree. And we're going to put the whole quartic polynomial in here. We're going to do a polynomial division. Long division. Okay. So what you do with any kind of division, even with numbers, you basically just focus on the front bit and say, what would I have to multiply x squared by to change it to x to the fourth? Well, I would need to multiply this by another x squared. So up here somewhere, I'm going to write x squared. I'm going to write it over the x squared term that's already here just because I like to keep my like terms lined up. It's not really going to make any difference. But when you do long division, you figure out how many times does this go into this, and you write the number up here. Then the next step is to take this number, the first start of your quotient, times this piece out here and write it underneath. And then the last thing we do is subtract. So I'm going to take x squared times all of this term by term. So x squared times x squared is x to the fourth. So I'm going to write that right down here, x to the fourth. And then I'm going to go to the next one. X squared times negative x is negative x to the third. Negative x to the third. Okay, then I'm going to do one more round, x squared times the last piece. So that's negative 2 times x squared, which would just be that, negative 2x squared right here. All right, so when I multiply x squared times another quadratic with x squared, I get this expression that has x to the fourth in it. Now, with any kind of long division, after you do that multiplication, we're supposed to subtract what we got from the row above. Okay, so when we subtract, of course, that just is the effect of changing the sign on everything. You get a different sign here. So that'll make this one negative, that'll make this one plus, and that'll make this one plus. So when we subtract, that's what happens. It switches to signs. And then this is why I like to line up the like terms. So when it's time to add or subtract, we can clearly see what goes on here. So x to the fourth minus x to the fourth makes 0. This should happen when we do problems like this, if we know this is supposed to divide evenly in here. If I do negative x cubed plus x cubed, those also cancel. And this is really what I'm after, this term. So I'm going to get a 23x squared plus a 2x squared. That's going to give me 25x squared. So it was a negative when I did the multiplication, but then I subtracted the negative, and so it becomes a plus 2 right here. Okay, so that's round one. I figured out something to write up here by asking myself what times this piece gives me the first term in here. Write that up here and then multiply it through, write those terms underneath, and then subtract each term from the line above, which is flipping the signs, and then you should have one piece left right here. Okay, so I only have to do one more round of this, I think. So what I'm going to do now is I need to form an entire quadratic expression out here to work with this. So I'm going to bring down the remaining two terms. So minus 25x minus 50, just bringing those straight down so that I have a complete quadratic expression here to work with up here. And if you'll look, I don't know if you can spot right away, but if I just multiply this by 25, I get all this. But just look at the front piece. What times x squared produces 25x squared? Well, I need to multiply it by 25. So that's what goes up here. Positive, so plus 25. And then this should completely cancel out because this was supposed to be a factor of this larger thing. So it should be the case that when I do all the multiplication and then I subtract, everything cancels out to 0. So let's multiply the 25 through this outer piece again. So 25 times x squared is 25x squared. 25 times negative x would be negative 25x. See, it's all matching up. And then negative 25 times negative 2 would be negative 50. So all of these exactly match. So when I subtract the lower line from the upper line, they all cancel out and make 0. That means there is no remainder, which means they did not lie to us that these two zeros, what were they? -1 and +2. If I showed the factors that are represented from those zeros, multiply those factors together to get a bigger factor, this should divide evenly into the original polynomial, and it does. So right now what we have is, this is telling us the original polynomial, which I'm not about to write out again, that big all long f to the fourth thing. When there's no remainder down here, it means these two things are factors. So it means the x squared minus x minus 2 times whatever you have up there. This is another way to represent our original problem. Now we also know that this one can break down into those two that I had earlier. I don't need these two anymore, so I could call it this. But this one, it still has x squared in it. So what that means is there's two more factors I can get out of this that just have x to the first. Because since my original polynomial was an x to the fourth quadratic, I need to have 4 individual linear terms, linear meaning x to the first in here. This one's x squared, so I need to break this one down into 2 pieces. So I'm going to go over here. I don't know any other factors to deal with, but with all quadratics, I can take any quadratic and set it equal to 0 and solve that expression. And that's what we're doing when we're trying to find the factors. We're trying to find the numbers that make that turn into 0, and that's how we can break down our remaining factors. So you could run this through the quadratic formula if you're just really into that thing with 0 for your b value. I think I'm going to do it a simpler way since there's just the x squared term here, no x term. I'm going to move the 25 to the other side like that and solve this just using a square root on both sides. And when you're solving a quadratic like this and you're doing square roots on both sides, you always have to remember there are two possible results, the positive and negative square root of what we've got going over here. So the plus and minus is when you're solving a quadratic using a square root. You have to account for both signs. And then here I can simplify. The 25, of course, is 5, but because it's negative, that means there's going to be that imaginary I piece to this. So anytime you have a term that has got an I in it, that means it came from the square root of a negative number. So these are my remaining two zeros. So the remaining, when I talked about the complex zeros, complex means it could have an I piece in it. So the remaining two zeros are positive and negative 5i. Okay. So as far as answering the first part of the question, so we have x equals negative 5i and x equals positive 5i, in addition to the two they gave us to begin with, which was x equals negative 1, x equals positive 2. So this original fourth degree polynomial has four different zeros. We have negative 1, positive 2, and then we also have negative 5i and positive 5i. So the first part of your homework assignment that just says find the remaining complex zeros, you would just find the breakdown after you've done the long division, whatever pops up here, that contains the remaining two zeros. How do you find a zero? You always take whatever you're looking at and make it equal 0 and then solve it. In this case, we're going to get two complex numbers. So the two remaining zeros would be those imaginary terms, positive I, 5i, and negative 5i. So those are my two remaining complex zeros. Okay, now how do we put this all together to write the thing in factored form? Well, we're going to do the same thing to form factors here that we did with the other two factors. So since I knew that a 0 was at negative 1, that produced a factor of x plus 1. A 0, they told us, was 2, so it produces a factor of x minus 2. Same thing for this. If I want to know what the associated factors are that go with those zeros, I basically just change the sign. So if negative 5i is a factor, then x plus 5i, if negative 5i is a 0, then the factor is x plus 5i. It doesn't really matter because it's going to produce the same idea. If 5i is the 0, then x minus 5i is the factor. So those are the remaining two factors. So here's the first two that they gave us when they just gave us two zeros. To find the remaining zeros, I had to go through and do this long division and see what popped out up here. Then I have to take this and make it equal to 0 and solve that to find the remaining two of the total four zeros. Once I know those two zeros, I can change them to factors by just altering the sign in front of the 0 like that. And then the last thing it asks us to do is to summarize what we've just done, which is I'm going to write the thing in factored form using these zeros. Okay. Well, two of the four factors, so there's going to be four factors. 1, 2, 3, 4. That's because we had x to the fourth. It was a fourth degree polynomial. So there could be as many as four of these that start off with just x, and. Okay, so if they told us a 0, great. So negative 1 means x plus 1 is a factor. If the 0 is positive 2, x minus 2 is the next factor. We did all of this to come up with our last two factors, or negative and positive 5i. So negative 5i was the next 0, so plus 5i, x plus 5i would be the third factor. And then if we say positive 5i was a 0, then x minus 5i would be the remaining. So this is the same as this expression, but it's just all broken down into factors. So if I were to check my answer, I absolutely am not going to do that, where I multiplied these two together and I get this thing, and I multiplied these two together and I get this thing. If I multiply this times this, it's supposed to give me the original problem. But I'm just going to let you do that if you want to for practice. So that's basically, you asked me how to get what was it called? The reduced polynomial. This part would be the reduced polynomial. Once you take your original polynomial and divide it by the factors that you have been given. Since they gave us two zeros, we were able to form the two factors from the two zeros and multiply them together. So this piece right here is the first two factors they gave us when they told us that the zeros were -1 and 2. You do the long division, what pops out on the top is what you call your reduced polynomial. It's been reduced because we took the original one and divided out the piece that we were able to identify from the information they gave us. We had to do a long division. This is your reduced polynomial here. So when you get to your reduced polynomial, that is what you're going to set equal to 0 to find your remaining zeros. And your remaining zeros can then be converted into factors just by altering the sign and putting an x in there with it. Okay. And then if it wants you to write the entire polynomial in terms of factored form, you would include the two that you just figured out at the end and the two that you were given at the beginning once you change the zeros into the factors, and then just string them along together. Those are your four factors that are represented by this original polynomial. Okay, so I hope that helps. Let me go ahead and get this uploaded so I can get it sent to you.